and we'll move on to
Thank
Joel
you.
Carlson for the last talk of this set. So, Joel, you should be able to share your
Thanks.
screen.
Yes, 1 second. Right, can you see my screen?
Yes. Okay, and so Joel will tell us about quantum Liouville cosmology.
All right, thank you. So yeah, since the 1980s, when Hartle and Hawking came up with their proposal for the wave function of the universe, there's been a need for tractable models of quantum cosmology to put the framework on more solid theoretical ground. For instance, you could ask whether such a wave function exists beyond the semiclassical approximation. There's also the question about the Hilbert space structure in cosmology and how to compute probabilities for observables relating to the issue that, at least naively, the Hartle-Hawking no-boundary wave function predicts very few e-folds of inflation. And to address some of these questions in this talk, I will forego observational and phenomenological constraints in favor of a model under better control. So I will tell you about a theory known as Timelike Liouville theory. This is a two-dimensional toy model of quantum cosmology. And let me just contrast to JT gravity, since we had a talk about that just a minute ago. The main difference here is that the Ritchie scalar is not constrained off shell to take a particular value. It can sort of fluctuate off shell. This model has local propagating degrees of freedom. It has a conformal mode problem very similar to that of higher dimensional Euclidean gravity. And it admits a semiclassical limit with features similar to Einstein gravity with a positive cosmological constant. At the same time, it has a well-controlled loop expansion, and this has been pursued up to the 3-loop order on the sphere. And it's a conformal field theory amenable to exact bootstrap techniques. And recently, it's also been seen a surge of interest from the mathematics community, where they're attempting to define its path integral rigorously. And yeah, given this rich list of features, we accept reducing the dimensionality of the theory down to 2D. So what is the theory? What is Timelike Liouville theory? Well, the starting point is a conformal matter system coupled to a dynamical metric. There's the topological Einstein-Hilbert term in 2 dimensions and a cosmological constant term with positive lambda. And upon gauge fixing, writing the metric as a Weil factor times some fiducial background metric G tilde that we can choose by hand, this path integral factorizes into 3 sectors. The BC ghost system from bosonic string theory, the matter CFT, now on the fiducial background metric G tilde, and the Liouville sector, which captures the dynamics of the conformal mode phi, or also known as the Liouville field. Since the left-hand side here, the gravitational theory should be independent of what fiducial background you choose, the total central charge of these 3 sectors combined have to add up to 0. The Liouville sector can be formulated in terms of this path integral here. And the dynamics for the Liouville field doesn't come from the Einstein-Hilbert term, since that's topological in 2D, and instead it's sort of emergent via the conformal anomaly from the matter CFT and the ghost system. And note here the sign in front of the wrong sign, so to say, in front of the kinetic term, and that's the conformal mode problem that I mentioned on the previous slide. The semiclassical limit of this theory corresponds to taking the central charge of the matter CFT to be very large. We consider unitary matter CFTs, so C has to be positive. But this means that the central charge of the Liouville sector goes to -infinity. So in and of itself, the Liouville sector is non-unitary, but that does not imply that the full gravitational theory with all three sectors is not needed here. And in this theory, you can construct wave functions similar to the one conceived by Hartle-Hawking as integrated disk one-point functions. So here, O is a scalar matter primary from the matter CFT sector, and it's stressed by this Liouville vertex operator to make the insertion gauge invariant. And these wave functions have been studied last year in a sort of gauge-fixed mini superspace-like Wheeler-DeWitt analysis that gave rise to these two linearly independent Bessel function solutions, one of which have a Hartle-Hawking-like behavior, decaying at small spatial slices and oscillating in a WKB-like fashion at large spatial slices, whereas the other one is more of the Vilenkin type. But these wave functions can be systematically analyzed without any sort of mini superspace approximation from the point of view of the path integral. And at the saddle point level, the two Bessel functions are captured by these spherical cap saddles, a small spherical cap and a large spherical cap, at least when the weight of the vertex operator is sufficiently small as to not back react on the geometry. In the paper, which will hopefully appear on the archive next week, we also consider heavy vertex operators that do back react and create the conical singularity in the geometry. At the quantum level, the boundary conditions for the Liouville field are crucial. The wave function only factorizes into these three sectors, the ghost, the matter CFT, and the Liouville sector, if the boundary conditions respect the conformal invariance. And this means that you cannot impose Dirichlet boundary conditions on the Liouville field. Instead, you can fix the physical proper length of the boundary of the disk, or alternatively, the conjugate variable, which is the trace of the extrinsic curvature of the boundary. And with these latter boundary conditions, the Liouville field is allowed to fluctuate freely without any constraints, both in the bulk of the geometry and at its boundary. And this gives rise to two zero modes, which are associated to non-isometric conformal transformations of the disk. So that's related to this moduli space of saddles on the left-hand side of the slide. And there's also, in addition, one negative mode. And this is a rotationally invariant mode. But whether it's a bulk fluctuation or a boundary fluctuation depends on whether the saddle is the large spherical cap or the small spherical cap. And this means that in the fixed length ensemble, these two potentially competing saddles come with different phases in the path integral. So the one loop result for the wave function looks schematically like this. The phase here comes from these negative modes and the zero modes. But the most important part is that the boundary condition, the trace of the extrinsic curvature, enters only through this particular combination in this gamma k symbol. And I will comment more on that on the next slide. But in this ensemble, when you fix the trace of the extrinsic curvature, there's only a single real saddle that contributes to the path integral. So when you relate back to the fixed L ensemble with an inverse Laplace transform, there are two potentially competing saddles in that Laplace transform, and which one you pick up depends on the choice of complexified contour that you integrate over. But the standard sort of inverse Laplace type contour parallel to the imaginary axis unambiguously chooses the Hartle-Hawking-like wave function. The theory can also be studied at fixed area, where instead of a cosmological constant, you insert sort of a delta function constraint into the path integral. And in this setting, it's much more similar to spacelike Liouville theory, which is, let's say, better understood version, like Timelike Liouville theory is the less understood version of the two flavors of Liouville theories. And it's been suggested in the literature that essentially these two theories are different real slices of an underlying complexified theory, but with different path integration cycles for the Liouville field. And in particular, our one-loop analysis suggests that the main difference is the integration contour for the area of the two-dimensional surface. In spacelike Liouville, you would integrate over the positive half line, but in timelike Liouville, there's a severe small area divergence, and instead you can choose these different complexified integration contours to recover the two linearly independent Bessel function solutions. So what have we learned from this analysis? Well, drawing from exact results in spacelike Liouville, a bootstrap analysis of timelike Liouville, the Wheeler-DeWitt analysis I mentioned before, and our one-loop analysis, we synthesized this all-loop or exact conjecture for the wave function in this Liouville theory in the K representation. And this form of the wave function, which is verified at the one-loop level, has a remarkable property. It suggests the following cosmological pairing, where you multiply psi of minus k with psi of k and obtain a k-independent result. At the saddle point level, you can sort of see why this happens, because you're gluing a small spherical cap to a large spherical cap to form a smooth two-sphere, and K controls where you're sort of cutting or gluing these two pieces together. But a priori, it's not at all clear that such a formula would continue to hold at one loop and beyond. But it resonates well with the quantum cosmology literature, where it's been argued that since these theories don't have an intrinsic notion of time, when computing probabilities, you should sort of identify one variable as a cosmological clock and not integrate over that when computing probabilities. And this suggests that K, this York time, naturally fills that role. It's also natural to ask how this might generalize to higher dimensions, and taking inspiration from recent developments in Einstein gravity on the manifolds with boundaries, it seems natural to fix, instead of not only fixing the trace of the extrinsic curvature, but also the conformal class of the metric on this gluing surface. And then one could ask whether path integrating over this conformal class of metrics also yields a k-independent results in higher dimensions. At the saddle point level, this still goes through, but it's not clear at one loop and beyond. And yeah, I think this would be interesting to investigate further, and we believe that this could yield further insight into the structure of the cosmological Hilbert space and gravitational path integrals in higher dimensions. Thanks.
Okay, thank you, Joel. Are there any questions for Joel?
I have a question.
Okay,
Yeah.
Kristen.
Okay. Right. So I'm glad that you mentioned this business at the end about trying to export these lessons to higher dimensions.
Yeah.
And can you comment more?
Well, yes, at this point, there's not that much more I can say, except that this sort of lesson, this sort of lesson kind of holds also in a one-dimensional toy model, so even more toy model than what we're considering here. Well, okay, yeah, maybe I can give one more comment in higher dimensions. So in higher dimensions, it's known that the de Sitter entropy receives a logarithmic correction with sort of a logarithm of a dimensionless combination formed out of the Newton's constant and the de Sitter length scale. And in fact, that logarithmic correction can naturally be understood to arise from this formula that I wrote down here at the bottom as well. Essentially, because the residual gauge group of this diff cross Weil gauge group of the gluing surface, which has one dimension less than the full sphere, has the same dimension as the isometry group of the sphere in one dimension higher. So that's sort of a first hint that something like this could work also in high dimensions.
Good. Okay, I agree. Thank you.
Thanks.
Okay, if there are no other questions, let's thank all our speakers today. And just before we do that, there are a couple of extra video talks. So those are available on the website for the seminar series, and I think they're already posted. And I believe that the video for this one will be posted very shortly afterwards. And so if you missed any of the talks earlier, you can go and check those out on the video. And otherwise, we'll see everyone sometime in the new year. Thanks for
Yes, and
coming.
the video are still not uploaded, but they will be within a couple hours.
All right. Thanks, everyone.
Thank you,
Thank you
everybody.
again.